Good afternoon, actually. So I'm going to introduce today's speaker, Dr. Sarah Ballard. She is a Sagan Fellow working over in the Department of Astronomy and with astrobiology, and she is one of our exoplanet hunters. And she got her Bachelor of Science degree in astronomy at the University of California in Berkeley, and working with Jeff Marcy. And if you know anything about exoplanets, you know that Jeff Marcy is one of the pioneers in finding extrasolar planets. And then she went on and did a PhD in astronomy at Harvard University, and is now here working in the astronomy department with Eric Agel. So let's. There you go.
Thank you so much. So I'm wearing two mics. Can y'all in the audience hear me okay? Okay. So I want to kind of take this opportunity. Erica was kind enough to let me come and speak to you. I think the seminar is on topics in NASA research, but if I only have 50 minutes with you, it's really important that I communicate to you this tremendous sea change that's taking place in exoplanets right now. And if you haven't been paying attention to what's been happening in exoplanets, in particular since January, I just want to just like pause for a moment and reflect. In the course of this talk, I'm going to really try hard to communicate the revolution which is occurring surrounding our knowledge of the rarity or lack thereof of Earth-like planets around other stars in the Milky Way galaxy. So, with that in mind, I kind of titled my talk "Planets, Planets Everywhere," but truthfully, that is the truth of it. That there are planets we now think around every single star, and this is something that I want to impart to you, given the year that you were probably born. So let's see. It's shameful to admit, I'm 28 years old. I was born in 1984. If there's any 20-year-olds in the audience that you were born in 1993 now, so you were probably close to the last generation of college students who were born in a time that when we did not know that there were any planets in existence besides the 9, now 8 so-called planets in our solar system. We thought, for all we knew, we were alone in the universe, and not because people weren't looking for them. We simply hadn't found one. And in 1995, we found the first one. So, any person who was born, are there any people here who were born after 1995? I mean, yeah, it's possible for folks who are alive today to be living in a time when we've always known there were worlds around other stars. That's a luxury of being a younger person now. So with that in mind, I'll kind of talk about planets, but bear in mind, I'm going to teach you some of the technical aspects of planet hunting, kind of review why those technical aspects inform our understanding of exoplanets and how they do that. But the overall message I want to impart is about the occurrence rates of exoplanets, about where those planets reside, what kind of stars they reside around, and what that means for life elsewhere in the universe, which of course is the driving question motivating me and I think other so-called exoplaneteers. I also want to emphasize during this talk that I love getting questions. I love getting questions in real time. Like no question is silly or something, and it was because of classes like this that I got involved in astronomy. I took like an Astro 10 type lecture at the University of California at Berkeley, which was for non-majors, and I absolutely fell in love with astronomy. So really, I started at the ground level, finding astronomy interesting, and I hope I can make it interesting for you all. So the first part that I want to emphasize, is there any way that I can also dim the lights? Is it shades? Half on? Nice, okay. So the first thing that I want to emphasize is certainly prior to 2009, and for the vast majority of exoplanet detections, you don't actually see the exoplanet. It's really easy to find that a little bit confusing, because in press releases, in news articles about exoplanets, they're often accompanied with these exquisitely rendered images of planets, and those aren't real images. So we as a species have no way of taking a picture right now of an extrasolar planet, which is not a very hot, very young Jupiter-sized planet. There's only 4 planets that have ever had pictures directly taken of them. So where does that leave us? When we detect extrasolar planets, we're detecting them indirectly, which is to say we detect them by the changes that they induce on their host stars. So, and in particular, the vast majority of planet detections have been conducted using 2 methods to indirectly infer the planets of stars. The first one is the one that's nearest and dearest to my heart that I'll be talking about in this talk, or I should say the second one, which has to do with the brightness variations of the star as a function of time. This method is called the transit method, and it's the one that I'll be focusing on in huge detail in this lecture. There's also another method that I'll kind of be glossing over in this talk, although up until 2009, it was by far the most fruitful metric to turn over exoplanets, and that was the so-called radial velocity method, which has to do with monitoring the movement of the star in space, rather than the changes in its brightness measurement. So I'll sort of reference those, but the method which pays my bills is the transit method. So this method is simple to explain, I think, and sort of mercifully simple to explain in astronomy. Sort of a way of like, if you want to buy stock in a concept that's easy to explain and yet has incredible richness in terms of scientific rewards for just the philosophy of the existence of life in the universe, invest in the transit method. Like, buy stock in the transit method. It is so simplistic to depict. And of all the things that have, you know, profound implications for humanity's knowledge of the universe, this is one that you can state in almost, you know, in 30 seconds. You know, so I've depicted this scenario at the top, you know, with the actual picture, which is something that we're never going to resolve, probably in my or your lifetime. Instead, what we have is this bottom graph. What we're measuring is the brightness of the star as a function of time. So each of these black dots is corresponding to an individual brightness measurement gathered by a telescope, perhaps on the ground, perhaps in space. As time goes on, we see that the star suddenly appears dimmer. I've shown on the y-axis the brightness of the star, like I said, as a function of time. If the star gets about 1% dimmer, that's corresponding to 1% of its light being blocked. The time of the transit tells us how long something was passing in front of that star. Such a signal, if it's a planet orbiting a star, occurs periodically. So the things that we can measure about the planet right from the beginning are, if we know the radius of the star, we can measure the radius of the planet, because we know that the planet blocks 1% of the radius, to kind of give you an understanding about what sort of planet would induce a drop in brightness by 1%. Does anyone know how big Jupiter is relative to the size of the sun? Are they equal in size? Obviously, no. Hopefully, yeah, they're not. And Jupiter is it's not half the size of the sun either. It's 10% the size of the sun. So you have the sun, a basketball, then you have Jupiter, roughly a golf ball. So, and that's in radius. So if you take the ratio of the areas, just as you do with pi r squared in a circle, the amount of area which is blocked when Jupiter passes in front of the sun is 1/100th, so 1/10 squared. So a Jupiter-sized planet passing in front of a sun-like star induces a depth of about 1%. So that's a good number to sort of keep on the top of your head for what state-of-the-art used to be. I'm going to show you this video. So this was gathered by the Solar Dynamics Observatory. This is an image of our sun. So if you've never seen, has anyone ever looked through welder's glass and actually looked at the surface of the sun? Those really dark pieces of glass. So it's not actually that exciting of a time to look through it. Usually if you look through very dark, never look at the sun, obviously, with your naked eye. If you look at the sun through welder's glass, you can see even with your naked eye that there are spots on the surface of the sun. You know, so stars are not perfectly opaque objects. They have all kinds of activity on them. You can see that the star has coronal loops. These are features of the magnetic field of the sun. You can see there are darker and hotter spots corresponding also to magnetic field on the surface of the sun. And our sun is also orbited by 8 planets and some extra chunks of rock. And in particular, the Solar Dynamics Observatory was watching the sun when Venus transited it. So I want you to pay attention especially to the relative speed of Venus passing in front of the sun versus the speed of the sun rotating. You know, so this video is sped up very much. The sun takes about a month to turn in one circle. You can see Venus is passing in front of it much faster than that. In fact, the transit of Venus takes about 10 hours to observe. So let's think about the probability of observing transits. So Venus is smack dab in the middle of the sun's habitable zone. If we were aliens looking in on our solar system and trying to detect an Earth-sized planet like Venus in the habitable zone of its star, then we would be trying to detect sort of a Venus-like planet. That would be very difficult for us to do on a planet that has a 12-hour night, for example. You know, so when you're limited to, so keep that in mind when I talk about detections from the ground versus detections in space, which really has made all the difference for transit exoplanet observations. That video is also exquisite. I love an excuse to play it. Here's another transit animation movie, just to kind of hammer the case home. This is a transit animation that was made for the press release of a hot Jupiter called HAT-P7. What you can see is that it looks about, a tenth the radius of the planet, give or take. So this is to scale. It's showing how close the planet is to the star. And as the planet passes in front of the star, the brightness of the star dims. You can see that there's also a little blip when the planet passes behind the star. There's a tiny fraction of light which corresponds to the planet reflecting light back at the viewer, which is lost when the planet passes behind the star. The vast majority of the transit signature constitutes when the planet passes in front of the star. Are there any questions so far? Yeah. Oh, yeah. Like, could you detect like an exo asteroid belt like around another star with the transit method? Yeah. It's actually really, so there are folks who have thought about that. In particular, you could detect, so your ability to detect things, it's much easier to detect small things that are orbiting really small stars, because what you're able to detect is just the fractional difference. So like an asteroid belt, asteroids are about the size of like small, like suburban areas, I guess you could say. They're like tens of kilometers or so. So your ability to detect a 10-kilometer transit of a thing, I showed you how hard it is to detect Jupiter. You could do it around a white dwarf, though. There are people who have been really interested in debris disks transiting in front of white dwarfs. It's very hard to do, though. But that's a good question. I'd love to talk about that more later, too. So this is an animation that I love, and I think that it really depicts well the sea change in exoplanets from the year 2000 until roughly today. So this is an animation that was produced by a professor at Princeton, Gaspar Bakos, who is responsible for the discovery of that planet animation that we just saw. And so he called this animation the well-tempered exoplanets. What I want to draw your attention to in the course of this animation is what happens between the years of 1999 and the year 2009. This is going to show exoplanet discoveries as a function of the year that they were discovered. So this is showing the mass of the planet that was discovered on the x-axis and the radius of the planet that was discovered on the y-axis. So to sort of orient you to the solar system objects, here's one Jupiter at 1 Jupiter mass, 1 Jupiter radius. Here's Neptune, which is about half the radius of Jupiter. It's about 4 times the radius of the Earth. Here's the Earth all the way down here. So keep the locations of those planets in mind. I'm going to first play the animation. So he called this the well-tempered exoplanets because he associated the appearance of each planet with a sound. I'll first play it with the piece of music by Bach that it was named after. And then I'll play it with the sound associated with the planets, and you can tell me truly which is more beautiful. So I want to draw your attention. I'm going to stop the animation right at 2009. And I want you to look at the types of planets that are discovered using the transit method. So you see the year is at the bottom right. So still 2002, there's 2. A handful. Okay. I'm going to stop the animation here right at 2009. This is showing the 30th of March in 2009, which was a very big week for exoplanets. And what I want you to notice is this is the sum total of all exoplanets which were known to transit in March of 2009. What you notice is those planets are most like which planet in our solar system? They were most like Jupiter. These were very, very hot planets too. The reason why they were hot Jupiters is because hot Jupiters, but when I say hot, I mean located very close to the star. They had periods of only a couple of days. They presented that transit signal every few days at the depth of 1% for a sun-like star, which we already saw, which was readily detectable for astronomers from the ground. So you had a 1% signature detectable with even an instrument that you could buy off the shelf. There are amateur astronomers who still follow up on the detections of hot Jupiters. The transit signal lasts 1 hour for a hot Jupiter in comparison with habitable zone planets around sun-like stars, which present much longer transits, like the transit we observed of Venus around the sun, which takes 10 hours. And those transits appeared every few days, as opposed to, how often does the Earth transit? Once every 365 days. These planets appeared not because they're the only planets that exist around other stars, but because they're easy to find. And you can see that it was only in 2008 or so that there were even the detection of 2 hot Neptune planets. So until March of 2009, what we had was only 2 hot Neptunes and a handful of hot Jupiters before the Kepler mission was launched. I'm going to play this animation for you now with the original sound attached to it. It's not very loud. I hope that you can sort of hear it. So what the professor did when he produced this animation was to associate with each planet a tone sound. The period of the tone, the distance between the tones, corresponds to the period of the planet, and the pitch of the tone corresponds to its mass. So an Earth-sized planet, so a Jupiter-sized planet, would have a very quick sort of bong, 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 bong. And an Earth-sized planet would be beep, beep. So sort of like that the distance is communicated, the distance of the planet from the star is communicated by that period. Let's start at the beginning. But still all Jupiters. Now watch what happens after 2009. That's a massive one. The launch of the Kepler mission. You can see by January of 2012, there had been many planets that were discovered which were nearing the size of the Earth. And the reason why that happened in 2009 was because of the launch of Kepler. So this is almost the sum total state of our knowledge in 2008. This was a paper that every astronomer who was interested in exoplanets that I knew was printing out and discussing in 2008. So this was a census of the known transiting exoplanets. This is half of the ones that were known. You can see, so the transit, which was actually detected, the shape of the transit is shown under each of these figures depicting the star and the planet to scale. Here was one of the single hot Neptunes that was in the bottom left-hand corner of that chart. Everyone who was anyone in exoplanets was studying GJ436 in 2008. Nowadays, you can't swing a purse without hitting a hot Neptune. And at the time, there was only known hot Jupiters. So this is how much our knowledge has changed. And it's all due to the Kepler mission. So I'm showing here an image from Cape Canaveral of the launch of Kepler in 2009. This is obviously showing the instrument to scale. It's a very simple instrument in the sense that it's just a single eye paved with silicon, staring unflinchingly at the same part of the sky for originally 3.5 years and now 8 years, because we've won funding for the extended mission. This is an image that I drew when I was a graduate student. I was taking Japanese, and I gave a talk about Kepler. So there's an artist's conception of a very happy Kepler instrument, which is discovering lots of planets. So the Kepler mission it's statistical in nature. So it's basically looking for that telltale blinking signature of worlds passing in front of their stars. It's monitoring 150,000 of these stars, and with an emphasis on solar-type worlds. Stars like the sun, looking for planets like Earth. So it was launched to address the question, how common is Earth among solar-type stars? But truthfully, even though that was the question it posed, the answer that it's come to is that Earth-like planets are common indeed, but not so common around sun-like stars as we thought. They're much more common around another type of star, which is what I'll be discussing. So what Kepler is able to detect by virtue of what you can infer from the transit light curve is the period of the exoplanet which is associated with the temperature of the planet. If you have a planet which is orbiting its star very quickly, it means it's close into the star and very highly irradiated, very warm, just as being close to a campfire warms you. If it's far away and presents periods relatively infrequently, it's much cooler. So here's the Kepler Field of view. It's in the constellation Cygnus. It'll be overhead in Seattle at about midnight in July. It's about the size of your outstretched hand. So you can see that it really is only a handful of silicon chips, collecting those particles of light as they fall onto the detector, the brightness measurements of 150 stars. So here's a close-up of the Kepler Field. You can see that in the original Kepler Field, there was 2 objects of interest which were known. There's trace to a single hot Jupiter lying within that field, which had been discovered by the TRACE instrument in 2008 or so. And here is our understanding of the positions of exoplanets now, after the Kepler mission. The New York Times called this diagram the Skittles plot, and you can see why they did that. These colors are corresponding to planets of a certain size. So you can see, for one thing, that there are many gas giants that were discovered, but in fact, they are not the most common kind of planet. It was only that we were heavily biased toward discovering them at first, because they were so easy to find. The vast majority of the planets Kepler is finding are Neptune-sized planets or even smaller. And truly, this is only when the mission, so this is from January 7th, this is truly only when the mission had been operating for about now half of its total lifetime. So Kepler is telling us that exoplanets are not rare, rather they are the norm. The mission has its work cut out for it. So you're truly monitoring stars, which are very variable objects. As you can see from even looking at our own sun, there's all kinds of features on the surface which vary with time. Stars present all kinds of crazy modulations. So Kepler's work is finding a needle in a haystack, but there are very dedicated people working on that. So let me draw your attention again to the 2008 exoplanet census. And here's the exoplanet census today. All of the planets which are just discovered by Kepler. And this is showing, again, the planets to scale against their host stars. So at the time of this press release, the number had gone to about 2,300 planets, a factor of 10 after the launch of a single instrument. Truly a remarkable instrument, I think, in the history of humanity for helping us understand our place in the universe. Something that I'm going to draw your attention to now is that this is the relative size of Jupiter transiting the sun. So you can see that the vast majority of stars which Kepler has found planets around are not solar-like or larger than solar-like. They are smaller. What's really remarkable about this fact is that nature produces small stars in such abundance. If you're interested in asking, as I am, ultimately, how hard will it be to go to another world where there might be other life? You're interested in the frequency of exoplanets, but really you're interested in how close is the nearest one? And this is a question I'm going to address at the end of this talk. If you're interested in planets that are nearby to Earth, you want to ask, how common are planets around the small stars? Because every 7 out of 10 stars that nature produces are very small. They're not like the sun at all, which is only maybe 1 out of 10. This is the most technical figure I'll show in this talk, so hopefully there's not, bear with me as I rush through this figure, but I think it's one of the most meaty figures from the Kepler mission. So this is a result in 2012. This is showing the occurrence rates of planets. This is the number of planets per star within some orbital period range as a function of the effective temperature of the star. Here's the sun. Here are planets hotter than the sun. Here are planets cooler than the sun. These different colored lines are corresponding to the colors of planets. Are corresponding, to the sizes of the planets. I'm highlighting now this range from 8 to 32 Earth radii, which is roughly Jupiter size and larger. Look at how rare these are, especially around sun-like stars. There's about 0.01 planets per star. We had to look at 100 stars to find a single hot Jupiter. And this led us to conclude that exoplanets were rare. But in fact, we were just looking in the wrong place, with instruments that were Earth-bound. Now we see that there is actually 0.2 or so planets per star around solar-type stars, if you add up all the different kinds. So you'd have to look at 5 solar-type stars to find a planet of any kind in orbit around it, and that's just a lower bound. This is only planets with periods less than 50 days. So there might very well be planets with longer orbital periods. But the most exciting part of this figure, the line that everyone was talking about when this paper came out in 2012, was this yellow line, and why it seems to increase for the small stars. Look at how small stars host twice the number of these small, potentially rocky planets as compared to solar-type stars. In fact, there's 0.3 small planets per so-called M star in this final period bin. All of a sudden, people who studied M stars were finding that their work was in very high demand. So to put this another way, 0.3 planets per star around an M star. So you would have to visit 3 nearby M stars to find 1 planet in a period less than 50 days. In 2013, in January of 2013, these numbers were updated with another year of the Kepler data. A graduate student at Harvard and a friend of mine, Courtney Dressing, was able to search for planets as small as half the radius of the Earth. So she selected just the Kepler light curves, which were the most exquisite, amenable to the most precise measurements of the stellar brightness, and looked at those to find the commonality of small planets around stars. And she found that fully 1 planet per star of any type resides around M stars. So there was another 0.7 planets per star, roughly speaking, an additional 7 planets in a collection of 10 M stars, which were just smaller than she was able to detect before. M stars host the small planets. If you're interested in planets which are just close to the radius of the Earth, so what we thought in 2007 is perhaps that there were bodies, so-called super-Earths, that could be between 2 and 3 times the radius of the Earth, and these would be rocky in composition. We don't have any planets like that in our solar system, but who's to say they don't exist? Now we sort of know they don't exist. Planets which are larger than 2 times the radius of the Earth have a large gaseous envelope on top of them, like Neptune or Jupiter. For whatever reason, nature makes that so. So if we're looking for life which is similar to the life which evolved on the Earth, you're not looking for, as Carl Sagan called them, octopi sort of swimming in the atmosphere of Jupiter. You want a planet with a rocky surface, with an atmosphere which is just the right thickness, where life could evolve in a tepid puddle of water. You know, it doesn't sound glamorous, but such are our origins. So we're looking for planets which are Earth-like. And if you're looking at just that radius range, there's 0.5 planets per star. Now you only have to go to 2 M dwarfs to find 1 planet which is the size of the Earth. But you might ask, where does that planet reside? I'm interested in planets only in the habitable zone, not planets which are too hot to sustain liquid water. Well, then you find that there is 0.15 Earth-sized planets in the habitable zone per star. So you basically only have to visit 7 stars to find a planet which is Earth-size and resides in its star's habitable zone. Well, where could that star be? You know, we don't yet know, because Kepler is only observing 150,000 stars outstretched, in the northern sky, and those stars are very far away. Kepler is not a targeted search, looking only at our nearest neighbors, but we know now statistically from the Kepler mission that this planet must exist, which is why the launch of the so-called TESS mission, which is being launched in 2017 and just earned funding a couple of weeks ago, is so crucial. So the promise of Kepler is that there's an Earth-sized planet in the habitable zone of a small star in our backyard. Where that planet is will be the work of TESS. So this is a figure I'm showing with just our nearest neighbors. So this is a quote from Courtney Dressing, my fellow exoplanetarian friend. This is showing all of the stars that reside within 10 parsecs of the Earth, so roughly about 30 light years. Remember I said that you have to visit about 7 nearest stars to find an Earth-like planet in the habitable zone of a star. This is showing the enormous number of small stars. These stars are color-coded to correspond to their temperature, where red stars are the cool stars. And you can see how common they are. Indeed, they comprise about 75% of the stars in our galaxy. Look at how close that world probably is, with the sun in its center. What's crucial, of course, is that such a world transit. And then we have to go out further still, because not all planets that exist around their stars transit, of course. You have to have just the right orientation. So in order to ensure that such a planet transits statistically, you have to go out to about 31 parsecs. So this world probably exists within this range, very close into our own sun. But to transit, you probably have to go a little bit further out. So this led folks to come to some conclusions in January at the Long Beach meeting of the American Astronomical Society, which is where Courtney Dressing spoke about her work. So here's the Kepler Search. Here's our sun in the suburbs of the galaxy, staring at 150,000 stars slightly above the galactic plane. But the truth is that we can infer numbers of planets that exist in the galaxy using the statistics that Kepler offers us. So this was what the press picked up, that there's probably 100 billion alien planets filling our Milky Way. Well, how could you come to that conclusion if you've only monitored 150,000 stars? The answer is because there's roughly one planet per star. Not all stars are M dwarfs. Our galaxy is home to 200 billion stars. They guessed roughly one planet per star for the M's, and then, they rounded down and came with 100 billion for this press release. Imagine 100 billion worlds. Is that not a truly astounding thing? And that's only in our own galaxy. It's incredibly moving to me, and especially the likely location of this nearby potentially habitable world to us. Why haven't we heard from that world? Have they heard from us? Such a world would just be now, in the sense of light years, receiving, whatever was playing in the 90s, Friends. We haven't heard anything from them. The question of whether or not life could evolve on that world is different. Although I'm sort of an optimist for the existence of life on other planets. So here's a pretty crucial figure that shows the so-called habitable zone as a function of the type of star. So you can see that there's solar-like stars. The sun is a G star. You get stars that are less massive and less luminous. As you go down on the y-axis, the habitable zone shifts inward. So that 365 days is a balmy room temperature around the sun, but you would have to have an orbital period of 60 days or so around a low-mass star to be just as comfortable. The habitable zone moves in. What about this tidal lock radius? Implications I think this class has already heard from Rory Barnes in the astronomy department about the importance of tides when it comes to habitability. When I like to think about M-dwarf stars, so here's us in Seattle. It's also very much easier to detect the so-called tugging of the star with the of the planet with the radial velocity method around small stars because they themselves are so much smaller. But that's just an aside that I'll make. They're advantageous for many reasons. But there are complications from living around a small star. And in order to really sum these up, I love to do a reading from Einstein's Dreams. Has anyone ever read Einstein's Dreams? Yeah. Einstein's Dreams is a work of fiction, which I think won the Pulitzer Prize. I can't remember if it won. It won some kind of literary award. It was written by a former astrophysicist called Alan Lightman. It's an imagining of what Einstein dreamed about in the years when he was a patent clerk and just learning to conduct physics experiments, which would go on later and win the Nobel Prize. But it involves sort of thought experiments about the nature of time. And when I think about worlds which could potentially be habitable and tidally locked, what we're talking about is a world in orbit around its star, which is similar to the moon in orbit around the Earth. The moon always presents the same face to the Earth. And a planet which was tidally locked to its star would always present the same face to its star. In practical language, that means eternal day and eternal night. Could life evolve on a world like that? Could you have life at just the terminator of the world, at the position of permanent sunrise and sunset? Could life evolve under the unflinching gaze of a star? These are questions which we don't know the answers to. And I think I like to appeal to folks' imagination about what life would be like on such an M star. This is from Einstein's Dreams, an entry from June 3rd, 1905. Imagine a world in which people live just one day, the human life occupying years and years on Earth, but only a single day around this star, since a day lasts forever. Either the rate of heartbeats and breathing is speeded up so that an entire lifetime is compressed to the space of one turn of the Earth on its axis, or the rotation of the Earth is slowed to such a low gear that one complete revolution occupies a whole human lifetime. Either interpretation is valid. In either case, a man or woman sees one sunrise, one sunset. In this world, no one lives to witness the change of the seasons. A person born in December in any European country never sees the hyacinth, the lily, the aster, the cyclamen, the edelweiss, never sees the leaves on the maple tree turn red and gold, never hears the crickets or the warblers. A person born in December lives his life cold. Likewise, a person born in July never feels a snowflake on her cheek, never sees the crystal on a frozen lake, never hears the squeak of boots in fresh snow. A person born in July lives her life warm. The variety of seasons is learned about in books. And such would it be in life around an M-dwarf star, where they would look at solar-type stars and wonder how life evolved on those stars. How funny that those creatures would encounter both day and night in a single lifetime. But that's the truth of it. And because we're only at the point now of learning about the occurrence rates of planets around stars, truly all astronomers now should be trained in biochemistry. How does life evolve? You know, this is a question which is much more complicated than the scope of people's careers, and let alone a single lecture. But I'm an optimist, like I say. So spin synchronization occurs around really small stars in the habitable zone, which is to say that the planet is presenting the same face to its star at all times. There's, if you've ever seen a picture of Io, the moon of Jupiter, it looks like a pizza. You know, it has incredibly active volcanic activity, which is due to the fact that the planet is so, the moon is so close to its planet that it's being tidally just excited to the point that it's actually warping, like the shape of a football, because of the differential force of Jupiter on one side of it versus the other. So, you know, a planet which is that close into its star, although that's not necessarily a bad thing, on Io it's bad. Who could live in a place which was constantly covered with volcanic activity? On the other hand, Earth's tectonic activity could be induced by something like tidal excitation, and tectonic activity is something that's crucial to the evolution of life on Earth. So again, not necessarily a bad thing. Small stars are also incredibly active. We know that the sun is a so-called active star. Sometimes, I know just recently, I think it was last week, the aurora borealis was visible, not from Seattle, but at other northern latitudes in the United States. In New York and in Maine, they could see the aurora borealis. It's very pleasant for us to have solar activity on the Earth. It's very pretty. Sometimes it induces problems with geosynchronous satellites. Then you get you know, sprays from the sun of highly energetic particles. We're guarded by our atmosphere, by the dynamo in the core of the Earth, which provides Earth's magnetic field and shields us from harmful charged particles. Around a small star, those stars are active for their entire lives. And we're not talking about activity that induces aurora borealis. We're talking about activity that could strip away the atmosphere of a planet. So it's possible that that could also be hostile to life, although whether or not it actually would strip away the atmosphere is work that's being done in the department at UW right now in astronomy in the Virtual Planet Lab. So in the time that I have remaining, I guess this is a good time for me to pause. I was going to talk about my own research for about 10 or so minutes. Are there any questions at this point that folks have? Yeah.
The lack of really large Kepler-like planets.
Yeah.
These other stars, I mean, all of our large planets are very far away.
Yeah, right. Yeah.
Kepler hasn't been up that long.
Yeah.
Do we expect more large planets to show up in the longer, orbit?
Yes. So there's two answers to that. The first one is that we wouldn't yet know for the really large stars. The reason why that's true is because we're depending on Kepler to find them. They're much less likely to transit because they're so far out. But if they do exist, we ought to pick up some of them. In fact, but they may just be less common. You know, in our own solar system, there's 2 really gas giant planets compared to the 8 planets which are smaller. So perhaps that occurrence rate is just about right. Around the small stars, we ought to have seen them already. The reason why I say that is because the transit method is not the only method which is looking for planets. Around small stars, a Jupiter-like planet produces a huge signal, which would have appeared in the radial velocity signature of stars. So all these same stars are being searched for radial velocity signatures. Around a small star, they would have shown up. The signature induced by the sun, on the sun by Jupiter, would be much harder to pick up. We might now be just seeing that kind of signature around a sun-like star. So the survey is sort of incomplete, as you say, for Jupiter-sized planets very far out around sun-like stars. They may exist. There are no Jupiters around small stars. Those would have been seen, and there's none. There's like one, which is really interesting about how nature forms planets. Are there any other questions? Did I miss something? Something you'd like to hear again? Okay. So I guess I'll conclude. This is work which is near and dear to my heart because I conduct it, but also because I had a press release today. So I'll be showing on the UW website a screen capture of that and make you all look at it. The reason why the existence of small planets in such abundance around low-mass stars is incredibly promising is because it bodes extremely well for the proximity of Earth-like planets, other Earth-like planets orbiting other stars to Earth. And I'll just sort of reflect for a second on the fact that when I was a graduate student in 2011, there was a seminar in Cambridge, Massachusetts that was held by sort of an exoplanet visionary at MIT. It was called The Next 40 Years in Exoplanets. It was a conference that you very rarely see as a student. It was a combination of famous astronomers and their graduate students, which were permitted to attend, journalists, and kind of like visionary type thinkers. So there were talks not only on the occurrence rates of planets, but on the possibility of traveling to those other worlds. It's my opinion that we won't ultimately be satisfied as human beings. Even if we discover another world which exists, which is Earth-sized and resides in its stellar habitable zone, we've characterized its atmosphere remotely, and it possesses signatures in that atmosphere of CO2, of carbon dioxide, so-called biosignatures, which could only be produced by organic forms. Even then, would human beings be satisfied? I would want to go. I would want something to go, a probe to go to hold an insect in our hand, for example. And there was a person there who was talking about how long it would take. With human technology today, we could send a probe to Alpha Centauri, the nearest star system which is known to have a planet. It would take about 40 years. You know, but there was a person there who was talking about whether or not you could extend human lifetimes, to extend a human being to that world. Anyway, these are the kinds of questions I think about when I'm falling asleep. So in any case, the promise of small stars is that they host so many small planets. The difficulty is that they are incredibly difficult to characterize. They're very hard to measure. And I've sort of glossed over the fact that in order to know the size of the planet, you have to know the size of the star. Of course, you have to know what is the size of the thing I'm blocking 99% of the light of. You know, if it's twice as large as you think it is, then the planet is twice as large. And as I just said, it's crucial that the planet be smaller than 2 times the radius of the Earth in order to have a rocky composition, in order to be plausibly habitable. So you have to be able to know the radius of the star. You have to be able to know its temperature in order to know the type of radiation which is bathing this planet that you discovered. Is it so close that any water on the surface would immediately be evaporated? Is it so cold that any water on the surface would be ice? Of course, we don't know that liquid water is necessary for life, but we have to start somewhere. And so in order to assess the habitability of these worlds, you have to measure the properties of their stars. This is very hard to do. There's the sun. And I've sort of highlighted, it's hard to see, this region in parameter space where it's very, very hard to detect something about the star. Why should that be so? It's really, really robust to take a spectrum of a sun-like star and infer things about it. The reason is because solar-like stars are very well understood. You know, they have hydrogen and helium, they have a radiative zone, they have a convective zone. We have machinery in place to produce synthetic spectra. So you put in the radius of the star, you put in the fraction of metals in the star, you put in the age of the star, and you get out a synthetic spectrum, which is to say all the light of the star spread out with a prism so that you see the light which is produced at each wavelength. You measure the spectrum of a sun-like star, you produce a synthetic spectrum, you tune a few knobs, and you say, this star is 1.05 times the radius of the sun. This star is 5,860 Kelvin, close to the radius of our sun. This is not possible for low-mass stars. So you have to play, they're coolers, they have grains in their atmospheres. They're entirely convective, south of about 0.4 times the mass of the sun. You know, so they're very difficult to model. You can't do this. So how do you measure their radii? And I thought of a way. So now this is a shameless plug for my own work, but this is supposed to be about NASA research, so this is just today. So what I did is I used so-called characterization by proxy. This work is reliant on the exquisite work which has been coming out of a young woman named Tabitha Boyajian. She's a so-called Hubble Fellow. Now she's at Yale University. It looks like stars are point sources, but of course they aren't truly point sources. They're very far away, but they do have an angular size to them. Just like if you were to look through binoculars at Saturn, when Saturn is up, I think Jupiter is actually up at nighttime right now. If you looked through a pair of binoculars, you could see that it's a disk. Stars are the same way. It's just those disks are so small, they're so far away from us, that resolving them on the sky, actually figuring out how much angular space they occupy on the sky, is extremely hard to do. But it's not impossible. And there's a woman at Georgia State and now Yale who's done this for a number of small stars that are our nearest neighbors. So she has taken this precious pool of nearby stars, some of which I'm arguing produce identical spectra to stars that host planets, and directly measured their radii, directly measured their temperatures. So I've done this characterization by proxy, where I took the planet that hosts a star 900 light years away. I argued it's extremely similar to these 4 stars in our backyard, which have directly measured radii and temperatures. Therefore, the planet is 2 times the radius of the Earth. Therefore, it is habitable. I suppose I'll skip over this slide. I don't have very much time left. So here's sort of my final slide, the second to final slide. This is showing the spectrum of the planet host star. KOI stands for Kepler Object of Interest. So it's one of the planets that hosts something 2 times the radius of the Earth. I said, wow, the spectrum looks almost identical to that of this nearby star, HD 88230, a random phone number. It possesses a measured radius and temperature. And so I was able to infer, sure enough, properties of the planet. And I'll close with this slide. This is showing all of the planets which have been discovered by the Kepler mission. The color corresponds to where the information came from for which I plotted them here. The equilibrium temperature, here's room temperature, and the radius of the planet. Look at this embarrassment of riches of planets around small stars discovered by Kepler. And there's Kepler 61, the one that I characterized, and that came out just today. It ended up being a little bit larger and hotter than we thought because of the characterization by proxy method. But I think it's a good place to close, just reflecting on the cachet of incredible, possibly habitable worlds. So thank you.
Okay, so we had one question from the chat. I'll start with that.
Oh, great.
Before you go into those. There was a viewer who wanted to know what is the most Earth-like star that's been found, and what are some of its properties?
Oh, so the most Earth-like planet which has been discovered to date was announced just last week. It was actually discovered by the Kepler mission. It has the designation Kepler 62. The star hosts 5 planets. It's smaller and cooler than the sun. So those planets are all intermediate in size between the Earth and 2 times the radius of the Earth. So there's nothing like that in our own solar system. We have rocky planets interior to the asteroid belt, interior to the orbits of the Jovian planets. Those things are all Earth-size and smaller. Then you jump up to the size of Neptune, which is 4 times the radius of the Earth. So there's nothing in between, which is between 1 and 2 times the radius of the Earth. What are the properties of those planets? Well, this system hosts 5 of them. One of them is 1.5 times the radius of the Earth, so-called Kepler 62f. So it's probably terrestrial in composition and resides right in the habitable zone of its star. That is by far the most Earth-like planet which has been discovered. So there are also smaller planets which are the radius of the Earth, so smaller, but they reside too close into their host stars to be possibly habitable.
Any other questions?